So I'm going to start off with an extension of, well, one of the questions from yesterday. So what does it mean for a quantum field theory to be Lagrangian? So this is kind of a preliminary detour. So in quantum field theory, switch markers. So in a quantum field theory, there are a collection of operators in the sense that Andy talked about. And some prescription to calculate so-called correlation functions. Of products of the operators. Now, these may be local operators, depending on a point in space-time, in which case such correlation functions tell you about scattering processes in the quantum field theory. If the theory is Lagrangian, or rather the theory is Lagrangian, if there exists a set of fields schematically phi a Lagrangian density L depending on phi, possibly derivatives, other coupling constants. And finally, a map. From the space of operators to the space of fields. Sending, for example, some operator OA to some functional FA of the fields. Sorry, it's a map from operator to functions on fields. Thank you. Well, I'm right. I mean, even that's not entirely correct, as we'll see in a second. But right, so you want these three things such that the correlation functions can be expressed as path integrals. So an integral of e to the I times the action with an insertion of these functions fa1 through fan. And if the space is not compact, then there's some normalization here. So one usually divides out by the path integral with the identity operator. Okay, that's so that's not fully general. What one has more generally on the right-hand side of this map, operators may either get mapped to fields or to some singular boundary conditions for the path integral, requiring fields to have a particular kind of singularity on some locus. And those things are called disorder operators, and one generally has both. If the theory is free, Meaning that the Lagrangian is quadratic. In the fields, the equations of motion classically are linear and decoupled.
Maybe you can clear up something for me. I always get confused why this order operator is just on a specific kind of field. Like, can't you just multiply by some field with the appropriate bad asymptotic behavior that you want?
Not always.
Okay.
You can you might hope, and I'm not sure this is always true either, that you can insert some local degrees of freedom at the disorder locus. Say if it's a line operator, you insert a quantum mechanics along the line, so that integrating out the quantum mechanics, doing the quantum mechanics path integral first, leads to a singularity in the bigger path integral. And so in that sense, you can get some kind of map from operators to honest fields, but it's really not a map to fields. It's a map to quantum field theories supported on the disorder locus. In some cases, including the theories, the 3D n equals 4 theories that I will focus on, there are operators in a gauge theory that whose insertion has the effect of forcing a singularity in the fields, and so that can happen, but it doesn't always.
The disorder operators are something like homology classes, and they become singular in trivial as almost any class.
Sure. I mean, yes, sometimes they can be smooth. Sometimes they can be smoothed out, but usually, I mean, not generally.
There could be a topological abstraction.
Right, which is the cohomology class. But
Also makes sense.
yeah. Okay, and so I am going to defer further questions about disorder operators to Kevin's talk. Okay. So I did want to say, so if the theory is free, it means that the Lagrangian is quadratic, the equations of motion are linear, and then the quantum theory can be solved exactly. The path integral is simply quadratic, so one can do the path integral. If it's weakly coupled, then the Lagrangian is quadratic plus some small corrections. And so one can hope to do the path integral in perturbation theory. In other words, Feynman diagrams. Whereas if it's strongly coupled, L is quadratic plus large. The non-quadratic stuff dominates, and all bets are off. There's no reason that perturbation theory should work. Nevertheless, one might hope to gain some intuition about the theory from formal manipulations in the path integral, which is still valid. Now, right, so to some extent, the classical Lagrangian might be considered meaningless in that its classical solutions really have nothing to do with the strongly coupled quantum theory. On the other hand, as I said, the path integral still makes sense, and one can do manipulations to gain some knowledge of the properties of the theory. And finally, I should recall that in a quantum theory and even in a classical one, the notion of weakly or strongly coupled depends on energy scale. Most prominently when the couplings are dimensionful, then it's only the ratios to the energy scale that we measure the theory at that actually matter. Okay.
Is there an arrow point sticking out of a large line? No. What do we use there?
So how do you solve QCD at low energies? I mean, there are methods, but perturbation theory isn't the answer. So usually one uses things like maybe some other very, very different looking effective Lagrangians whose perturbation theory does accurately describe these theories to solve them. But the answer is not obvious. Okay.
Are there examples where the coupling constants are dimensionless?
Yes, there are, most notably in 4 dimensions. And so QCD is precisely such an example. The gauge coupling is dimensionless, classically. And in the quantum setting, it gains quantum corrections that give it an energy dependence. Okay. So that's the end of the detour. So today, I want to start talking about 3D theories with n equals 4 supersymmetry. The reason I want to do that is because these theories have a moduli space of vacua that contains, it's necessarily hyperkähler, and that contains typically 2 or more branches that coincide with the conical symplectic resolutions that I described yesterday. And Ben Webster tells me that it was almost 8 years ago that Sergei Gukov and Edward Witten pointed it out to him that there was a connection between 3D n equals 4 theories and the manifolds he was looking at. So I want to describe how that connection works. And let me recall from yesterday. So n is a conical symplectic resolution. If it resolves some affine cone, M naught, in a way that the holomorphic symplectic form is preserved. And one requires these to have a few extra properties. I will always want M and M naught to be hyperkähler. In particular, there are 3, there's a CP1 of complex structures, there's a CP1 of Kähler forms, but I've done 2+1 splitting. So one of the Kähler forms in the hyperkähler sense is a Kähler form in the complex structure I've chosen, and the other 2 Kähler forms combine to produce the complex one, the complex symplectic form. And I want the existence of 2 symmetries. So a U1 epsilon action on M that extends to a C star on M naught, which in both cases act on the symplectic form with weight 2. And second, in general, one wants an isometry group. I should call it GM. A group of hyperkähler isometries commuting with U1 epsilon such that some U1 in this group has fixed points, has isolated fixed points. That's what I was calling UNC yesterday. So some U1 has isolated fixed points. OK. So I want to explain how this setup arises in 3D n equals 4 theory. So we want to talk about theories in Minkowski space in 2+1 dimensions. So I'm going to be working on R21. The isometry group of Minkowski space is the Poincare group. SO21 semi-direct product with translations, where SO21 is the Lorentz group. And the Lorentz group has a double cover. That's SL2R in this case. Now, the n extended, and I should say I'm not going to be terribly careful about differentiating between groups and their covers. The n extended supersymmetry algebra in 3 dimensions is an extension of the Poincare algebra. So extends Poincare algebra with n odd generators. Which I'll call Q alpha A, where capital A runs from 1 through n, and lowercase a, alpha, runs from 1 to 2. And just designates components in a spinorial representation of SO21. In other words, a fundamental representation of SL2R. In particular, in 3 dimensions, the odd generators are real. So the algebra they obey is Q A alpha, Q B beta. The anti-commutator is equal to delta AB sigma alpha beta mu p mu, where sigma alpha beta are Pauli matrices. They give an intertwiner between the bi-spinor and the vector representation of SO21. So, or spin21 rather. So sigma, in this case, I can take sigma 1 to be 0, 1, 0, the identity matrix, sigma 1 to be 1 minus 1 on the diagonal, and sigma 2 to be 0, 1, 1, 0. And so mu is a space-time index. going from 0 to 2. And p mu are the generators of translations in R21. So the typical thing is that the commutator of supersymmetries is a translation. This algebra has a central extension. It has several, but if I want one that preserves Lorentz invariance, I can include some central generators, antisymmetric in the AB indices, times epsilon alpha beta. And now I should note that the algebra has an SON symmetry acting on it that simply rotates the Q's in a fundamental representation. It acts on the A indices. So the Q's are actually in a spinor of SO21 and a fundamental representation of this SON, and this is called the R symmetry group.
What does R stand for?
Oh. I have no idea. I have no idea. It's an R symmetry in any theory is one that acts on the supercharges. It doesn't. It's some global symmetry that does not commute with supersymmetry. Okay. In our case, we want n equals 4. So the R symmetry SO4 splits, again, modulo coverings, as SU2 cross SU2. And for reasons that will become clear throughout this talk, I'm going to call them SU2 Coulomb and SU2 Higgs. In this case, there are 6 central charges. ZAB has 6 components, 6 real components, an antisymmetric tensor. And they sit in as representations of SU2 cross SU2. They sit in an adjoint of one plus an adjoint of the other. Okay. Time.
Why don't we take ON? What is the plus or minus 1 boring or something?
No, it's so, I mean, right. So discrete you can ask. Let me remember and get back to that. So the discrete symmetry is usually considered separately in the theory, but so you get things like charge. It's called something like charge conjugation. Although I'm not sure that's what it is in this particular case. I need to remember and think about that. Okay. So as a side note, 3D n equals 4 is the 3D n equals 4 algebra is a reduction, is a dimensional reduction of 4-dimensional n equals 2, which is the supersymmetry of class S theories that Andy and David have been talking about. And the constraint that in an n equals 4 theory, all spaces of fields have to have some hyperkähler structure. I'll say in a second more precisely what that means. Is apparent in Andy's theories, where he takes a 4D theory, compactifies it on a circle, and finds a Hitchin moduli space of vacua, which of course has a hyperkähler structure. So now let me talk about fields and.
So are you going to explain at some point why Andy's theories, you see Hitchin moduli space, here you see something quite different with, isolated fixed points?
Yeah, it's because Andy's theories, wait, gets you something different in what sense?
I mean, here you have something which is, birational with optimization.
Yes. So, so it's because Andy's theories are not truly on R3, but on R3 times S1. And the radius in that compactification acts as, well, it gives you the size of the compact fibers in the Hitchin moduli space. And so, or rather the inverse radius gives you the size of the fibers. So if you take the radius all the way to 0 size and go all the way to 3 dimensions, the Hitchin moduli space decompactifies, and you get something more of the type that I'm discussing. Okay. And that basic idea was, I think, first in a paper of Seiberg and Witten's around the time of the Seiberg-Witten papers about compactification to 3 dimensions. That relation between moduli spaces on a circle and 3 dimensions. Hitchin systems were not exactly part of the story. But, yeah. Okay. So, right, what kinds of fields can we have in a supersymmetric theory in 3 dimensions? They come in collections related by the supersymmetry generators, so-called in multiplets. And there are 2 basic ones. There's a so-called hypermultiplet that consists of two complex scalar fields, or 3 or 4 real scalar fields. So I've written it in such a way that they're both complex. They're functions of the space-time coordinate. And in addition, there are 2 complex fermions. And they all get mixed up and related by the supersymmetry transformations. So acting on one of the scalars with a supersymmetry transformation gives a fermion, and then acting with another supersymmetry transformation gets you back to the scalars and so on. It gets you back to the bosonic fields. X and Y here, as I've split them, or rather X and Y dagger, are in a vector of SU2 Higgs. And so I've somewhat arbitrarily chosen one of the SU2s in the R symmetry group. It doesn't matter which one we choose. I will call it Higgs. And so the hypermultiplet bosons transform under it.
Sorry, I'm a little confused. So SU2 Higgs was acting on the supersymmetry generators, but now you're saying it's acting on
both. The action is compatible.
Okay.
So, right. Why is it compatible? So you start with, say, one of the real components of X, and act with a few supersymmetries. You'll end up with a component of Y, or one of its derivatives. For example. but if I use the R symmetry, I will change the supersymmetries that I'm acting with. And so I'll either get a different component of y or maybe another component of x. So precisely because the R symmetry acts on the supercharges, it also has to act on the scalar fields in the hypermultiplet. On R21, we can talk about a space of fields. Where I will mean the space of their values at a point. Or equivalently, the space of constant field configurations. It's this space that has to be hyperkähler in an n equals 4 theory. In this case, it obviously is. So the space for a hypermultiplet is just C2. Or more intuitively, it's better to write it as T star of C with the standard affine hyperkähler structure. In particular, the metric is dx squared plus dy squared. The Kähler form is I dx bar plus I dy bar. And the complex symplectic form is dx wedge dy. Again, I've chosen a way to split things into complex coordinates. Different choices of splittings are related by SU2H. There is, of course, a subgroup of SU2H that preserves the splitting, preserves my choice of complex structure. Call that E1H. Preserves the complex structure. And it rotates, or it rephases x, y, and the holomorphic symplectic form with weights 1, 1, and 2. Okay. I have decided not to talk about them.
It seems like we always do that when we talk about modulus fields.
Oh, sorry. That's because one is analyzing configurations with zero potential energy that preserve Lorentz symmetry, or that preserve Lorentz invariance. And in particular, that requirement of preserving Lorentz invariance tells you that you can't give a value to anything that's not a scalar. I think that may actually, I think that may come directly from requiring zero potential energy, but certainly Lorentz invariance does it immediately. So I have set them all to 0. Sorry.
This is a synonym for modulus is a vacuum?
Well,
No.
Sorry, your question was about moduli spaces of vacua. And when discussing moduli spaces, one sets all of the fermions to 0. In this case, if I don't care about the moduli space and I'm just talking about the structure of the hypermultiplet, there are fermions. They do transform non-trivially under SU2H and in fact also SU2C.
But secretly they pop up as like odd tangent vectors.
I mean, it depends what question one's asking. Yeah. Okay. Right, and then there's this thing called a vector multiplet. To describe it, I need to choose some compact group G, some compact Lie group, and then the bosons in the vector multiplet consist of a gauge field a gauge connection for G, a real scalar and a complex scalar, which are all valued in the Lie algebra. So locally, I'm thinking of the gauge connection as a Lie algebra valued one form. And it's, well, that they should all be valued in the Lie algebra because, again, supersymmetry is going to relate one component to the other, and supersymmetry commutes with the action of this group G.
So can you repeat what sigma and phi are?
Sorry?
Can you just briefly repeat what sigma and phi are?
They are a real and a complex scalar that have to exist whenever there's a gauge field in the theory by supersymmetry. And so there are also two complex fermions that, again, I won't say very much about. Now, so sigma and phi, viewed as three real fields, form a vector or a fundamental representation of SO3C. In other words, an adjoint representation of SU2C, identifying SO3 and SU2. The space of fields, again, is hyperkähler. It's easiest to see in the abelian case. So if G is U1, then the gauge connection can be dualized to a scalar in 3 dimensions, a scalar gamma, such that d gamma and dA are Hodge duals. This is very similar to T duality in 2 dimensions, where scalars are dual to other scalars. And gamma ends up being S1 valued. Rather, it's periodic. Then the space of fields, sigma phi gamma, classically live in R3 times S1. That's the right dimension to be something hyperkähler. The metric on it is d sigma plus I gamma squared plus d phi squared. The real Kähler form looks just like the metric, and the holomorphic symplectic form is d sigma plus I gamma wedge d phi. So again, I've chosen a complex structure in splitting phi and sigma into a real and complex scalar. And in terms of those, sigma plus I gamma and phi are complex coordinates. Cool. Now, there are several different kinds of 3D n equals 4 theories. They go under names like gauge theories, sigma models, and CFTs. The types of, in each case, the types of couplings that the theories are allowed to have and the Lagrangians that they have, if any, are severely constrained by the supersymmetry. The most important one for these talks is a so-called linear gauge theory, which I will usually just call a gauge theory.
Since we're having some discussion of reax, can you explain how you get these 2 different kinds, whatever, from different applications, if that's a cool thing? I think you maybe already said this for 2 of them.
So the a general theory in this class is not going to come from a compactification of theory X, for which I apologize. There are special gauge theories labeled by linear quivers that come from n equals 4 super Yang-Mills in 4 dimensions with certain boundary conditions that can be lifted up to a theory X compactification. And on Thursday, hopefully, I will reduce these 3D theories to 2 dimensions, where they also become equivalent to a certain reduction of theory X to 2 dimensions, in order to talk about Kavanagh homology. But a priori, not related. They are in the general universe of things one talks about when considering compactifications of theory X, but Okay, so right, so in particular, sorry, there's a very obvious way to get 3D n equals 4 gauge theories from X. Take a theory of class S that happens to have a Lagrangian gauge theory description. So that's X on a surface, and then compactify in S1
Okay.
all the way. You go to 3 dimensions, you get a 3D gauge theory of this type. Okay. So the basic data of a gauge theory is a gauge group G, some compact Lie group, and a quaternionic representation. An affine quaternionic representation, in other words, a vector space that looks like some number of copies of T star C on which G acts. Some copies of T star C have a hyperkähler structure. I want the hyperkähler structure to be preserved by the action of G. The fields in such a gauge theory consist of hypermultiplets xi, yi, I running from 1 to n, and vector multiplets or a vector multiplet in labeled by, well, containing the gauge field for the group G. Given that, there are only 3 types of parameters controlling the interactions in this theory that are allowed. As I said, the Lagrangian is severely constrained. So 3 types of parameters. One is a gauge coupling. For each factor GA in the gauge group. The gauge coupling in 3 dimensions, unlike in 4 dimensions, is dimensionful. It has dimensions of mass, and so the scale that we measure the theory at is going to change the effective value of the gauge coupling. In a very major classical way, even without talking about quantum corrections.
What do you mean by each factor of G?
So if G is something like, say, U1 times SU3 times SU4, there's a separate coupling for each factor. It comes into the action as 1 over G squared, as a term 1 over G squared F mu nu, where this is the kinetic energy for the field A. The reason it has dimensions of mass is because in 3 dimensions, the Lagrangian has to have dimensions of mass cubed, but F mu nu involves a derivative and it involves this gauge connection. The gauge connection always has dimension 1. The derivative has dimension 1, so F mu nu has dimension 4, and that needs to be canceled by something to get a 3 out. Whereas in 4 dimensions, it's dimensionless. There are 2 other, two other types of parameters. To describe them, let me consider a group GH of isometries, hyperkähler isometries, acting on the hypermultiplets T star C to the n independently of or commuting with G. And a similar group, GC, of isometries acting on the vector multiplet scalars, the vector multiplet bosons, independently of G. Now, the first one is easy to think about. The second one is a bit harder to think about. Classically, GC is U1 to the number of U1s, the number of U1 factors in the gauge group. So what happens is for every U1 in the gauge group, there's an abelian gauge connection which can be dualized to one of these periodic scalars, gamma. And the U1 in this isometry group just rotates gamma. Remember, this was periodic. Quantum mechanically, this can often get enhanced to something non-abelian, but classically, it's just a product of U1s. And the claim is that for every element of the Cartan, for every generator of the Cartan of GH and of GC, there's a triplet of parameters in the theory. And these are called masses on Fi parameters. So the theory has parameters M in the Cartan of GH and transforming in the adjoint representation of SU2C and Fi parameters. So these are called masses. These are called Fi's in the Cartan of GC and transforming as an adjoint of SU2H. Typically, I will split the masses into real and complex components. So in other words, split the adjoint of SU2C, where these just live in TGH and TGH complexified, and similarly for the so-called Fi parameters. Now, how do I think of these? Well, physically, whenever there's a symmetry in the theory, I can introduce a vector multiplet for that symmetry. And the m's and the t's, or rather MC and TTC, are values of scalars, just like phi and sigma, in a frozen vector multiplet, where the gauge field and all the fermions have been turned off, and phi and sigma and the scalars are just forced to take constant values throughout all of space.
You know, I think the last 4 sentences you said were just completely incomprehensible.
Great, thank you. That's very useful.
Can you make that more?
No, I probably, well, I don't know. If you're willing to buy that there exist these parameters, then I don't really need to explain how they arise.
Multiplet whenever when it's in.
Ah,
What does that mean?
well, so if I'm trying to build a Lagrangian for a gauge theory, I start out with some collection of hypermultiplets and some G action on them. And then I start thinking of these as sections of some bundle transforming under G, and turn on a connection for that bundle. And so in a gauge theory, the connection is just some new dynamical field. And supersymmetry tells me that when I have a connection, I have sigma and phi as well. Now, I could also introduce so that statement is to point out that whenever there's a symmetry, there is a vector multiplet associated to that symmetry, not just a gauge field. Now, I could have also chosen, rather than turning on a dynamical vector multiplet that has fluctuations, depends on space-time, I can turn on a constant vector multiplet. I can just stick it into the Lagrangian. Constant in the sense that A is set to 0, the fermions are set to 0, but phi and sigma can take some values. And that is automatically a supersymmetric interaction. And the values that I fix sigma and phi to take become parameters in the Lagrangian. They just become some constant parameters. And that's how the m's and t's arise. So the m's arise from a vector multiplet of the standard kind, where sigma and phi transform under SU2 Coulomb. And the t's arise from a so-called twisted vector multiplet, where I've just decided to change the R symmetry group that sigma and phi transform under, because there's a symmetry between SU2C and SU2H. That's the expanded version of the statement. And that's it.
I think this is physically naive, but I thought Fi terms are supposed to be like auxiliary, you just integrate them out immediately, like that's allowed. That's not how I think of masses. No, is that not right? Or are these not like the F terms of these Suzy Lagrangians?
No, never.
Oh, sorry.
They enter D terms in Suzy Lagrangians, but also a lot of the intuition about Fi terms that you might be familiar with comes from 4 dimensions, when they have nothing whatsoever to do with symmetries. In 3 dimensions, they're really on the same footing as the masses. And in particular, they are both massive. Again, unlike in 4 dimensions. So the dimension of the mass and of the Fi parameter, it's massive in 4 dimensions too. It's not in 2 dimensions. But the dimension of the mass and the Fi parameter is 1, just like the gauge coupling.
So like a really Poiseuille's view of mass, which means something that's massive, I take some limit in which its value becomes frozen. Is that how I should understand the word massive?
No, I don't mean any. Well, it's already. Sorry, the m's and t's are already frozen. What?
You've already taken that.
I've already taken that limit, and it has nothing to do with what I mean by massive here. Here, I just mean that they're dimensionful parameters.
But would you have been allowed to take that limit if they hadn't been massive?
Yes, it has nothing to do with. Yeah. It's completely independent. I can always add a constant field into the Lagrangian by hand. Often that constant field, well, sometimes that constant field might be coming by freezing out some dynamical field at high energy, but I can always just put it in by hand. Okay, and what time did I start and when am I ending?
You started at 11:30 and aiming to end at 12:30.
Great. I'm almost through half of the talk. Okay. One thing to ask about this theory is what are the space of vacuum configurations? So, for example, when parameters like the gauge couplings and M and T are turned on, what are the lowest energy values of the fields? Constant throughout space-time, but what values can they take to minimize the potential energy? So I'll use the vacuum, or in a supersymmetric theory, they're often called BPS equations. BPS equations are a little more special. They look for field configurations that are preserved by all of the supersymmetry transformations. And they take the following form in one of these theories. They look like the critical point classically in the classical theory. They look like the critical locus of a complex superpotential and a real superpotential divided out by the gauge group, which, because the gauge multiplets are dynamical, I I should quotient the path integral out. Well, I quotient out all of the fields by the gauge symmetry. So I'm only looking at field configurations modulo the action of G.
So
Yes,
G is the compact group or the gauge group?
both.
In this case, G is the compact group or the gauge group?
G is the gauge group, and it is a compact group.
Oh, I see. And you don't mean the infinite dimensional group.
Oh, sorry. It's the gauge group at a point.
Okay.
It's gauge transformations at a point. So in this case, the space of vacuum configurations requires fields to be constant throughout space. And so the only gauge transformations that are left are the ones that change their values everywhere.
Sorry, can you repeat what W and H are? Maybe I missed that.
I haven't defined them. So W is a complex superpotential. The splitting between W and H is somewhat artificial. It only comes about because I've chosen complex structures for vector and hypermultiplets. So it's a complex superpotential that takes the form of a sum of phi times complex moment maps for the G symmetry plus the complex masses contracted with complex moment maps for the GH symmetry plus the Fi parameters contracted with phi. And so all of the contractions make sense if one works through the various groups that everything transforms under. And phi is the classical moment map of the GC symmetry, of the symmetry on the Coulomb branch. H is the same thing with real parameters. So it's sigma times a real moment map for G plus M times a real moment map, I'll just call them mu's, for GH plus T times sigma. So again, let me remind you that on the hyperkähler manifold, there are, the way I'm splitting it, there are three Kähler forms. They combine into real and complex, and correspondingly, there are three moment maps for every hyperkähler isometry, real and complex, and that's what goes into H and W. Okay, and one. One last word on the general structure. So the what? If the m's and t's are both set to 0, then that moduli space described by what looks somewhat similar to a hyperkähler quotient but is not quite. The moduli space has at least two components. One of them is the so-called Higgs branch, where sigma and phi are set to 0, and the critical point equations really just tell me that I set the moment maps to 0. So mu g c is set to 0, mu g r is set to 0, and I quotient out by g. And so that's a hyperkähler quotient on the space T star of C to the n. So this is V quotiented out by G, and it's singular. This gives me a singular cone, an affine cone, just like in, say, the symplectic duality story. Let me call it MH0 because it's singular. There's another branch of solutions where the x's and the y's are set to 0. And again, I'm looking at things modulo the gauge group. So the invariant quantities parameterizing the solutions are eigenvalues of phi and of sigma. And once I've turned on a particular set, well, a particular diagonal configuration of phi and sigma, the gauge group is broken to U1 to the rank. It becomes abelian, and I can dualize the rest of the abelian gauge fields to get those S1 valued fields gamma, the so-called dual photons. So there are rank G of these, rank G of those, or 2 times that, and their rank G gammas. And so classically, the Coulomb branch looks like R3 times S1 to the rank of G modulo Weyl transformations coming from reordering the eigenvalues. Quantum mechanically, the Higgs branch is exact. There are no quantum corrections. The Coulomb branch is not. And it's essentially because of this presence of a gauge coupling. So the Coulomb branch gets quantum corrections that most importantly change its topology, but also change the hyperkähler metric on it. So that at low energy, so first changing the topology and sending G squared, sending all of the gauge couplings to infinity. So remember that they're dimensionful. They have dimensions of energy. So if I'm at very low energy, effectively, they are all sent to infinity. Then MC becomes another hyperkähler cone. And I will give you an example of that tomorrow.
Is there an explicit quotient description?
No. There absolutely is not. In some theories that have so-called 3D mirrors, there is a second gauge theory whose Higgs and Coulomb branches are swapped. And then there is, if there exists a 3D mirror, then there is a quotient description. But in general, there is not. It's in abelian theories, one can describe the quantum corrections to the topology and the metric explicitly and figure out exactly what this is. In non-abelian theories, it's very hard to describe the quantum corrections. There have been some explicit calculations in the past, and with Davide and Matt Bollamore, I think we have a prescription for any UN quiver theory to figure out the Coulomb branch, at least as a complex symplectic manifold. But in general, it's a very hard problem, and it is certainly not a quotient. OK, I'm out of time. Thanks.
Can you give an example of something that is not a quotient?
Yeah. Take a messy quiver variety.
Generic one.
Yeah. I mean, even I may not even need to get all that complicated, but this certainly will do the trick. So all right, so what is this? This is, so in class S, there are these theories called T of n, corresponding to compactification on a 3-punctured sphere of the 60 of theory X of type of type A n minus 1. And what I've drawn is the theory, well, so in 4 dimensions, there's a theory T3. That's compactification on a 3-punctured sphere. It's non-Lagrangian. It's strongly coupled. It can be compactified further to 3 dimensions. It's non-Lagrangian and strongly coupled. But it has a mirror in 3 dimensions, which is this. So it's very difficult to describe the Higgs branch of this non-Lagrangian strongly coupled theory Tn. And the Higgs branch is actually the same in 3 and 4 dimensions. And here it's very difficult to describe the Coulomb branch. There's no known gauge theory mirror of that.
Yeah. Can you just repeat the definition of the Coulomb branch? I think I missed what the conditions on the eigenvalues were supposed to be.
Yes. So I should have probably said what happens first in an abelian theory. So in an abelian theory, phi and sigma are neutral under the gauge group. One doesn't really have to worry about gauge transformations, and so one just gives them some values that parameterize part of the Coulomb branch, and then you dualize the gauge field to get this gamma. If in a non-abelian theory, so suppose that G is SU2, then you can give phi and sigma actually have to commute. That's one of the equations coming from the critical locus. So they can be simultaneously diagonalized. You diagonalize them. And at least for non-zero values of the eigenvalues, phi and sigma, the gauge group is broken to a maximal torus that commutes with these forms of phi and sigma. There's a gauge connection corresponding to this U1 inside SU2. That's an abelian gauge connection. It's part of the non-abelian gauge connection. And that thing gets dualized to an S1 valued field gamma that completes the classical description. So in this SU2 theory, the Coulomb branch is R3 parameterized by the eigenvalues phi and sigma times S1 divided by Z2 coming from the residual Weil symmetry. Does that help?
Okay, so there isn't a condition on the eigenvalues. You're just using the eigenvalues to put coordinates on the.
Yeah. That's right.
Are you going to say next time what exactly it means to have these quantum corrections? Like, what is this moduli space now that we're computing?
I will give very explicit examples tomorrow.
No, not examples, but the definition.
Of what?
Like before, the moduli space was the solution to the classical equation of motion. That was what we were looking at.
Yes.
What is it now?
It's a product of these things with quantum
No.
It's the spectrum of the ring of operators as the data set. And like the
Sure, right. So that's a lovely way to think about it. So in the
Okay, but then you're saying it's always that fine?
Well, you can consider like line defect. So you expect like line defects to be metric levels on this. So if you probe it with non-local operators, it's actually more like information.
Okay.
Local operators are only seeing the optimization.
it's
Okay, so can you define like what the entire thing is?
Medium principle.
We'll
so
see that tomorrow.
yeah.
Oh, all right, awesome. Okay, I commit. Like you'll give the metric and all of this also. Is that a logical metric? Like what is this?
Yeah. I mean, it's so we're talking about the moduli space of a CFT. So at low energies, this gauge theory where the m's and t's are turned off flows to a CFT. It has no dimensional couplings because the g's have gone to infinity and have dropped out.
Okay.
So this becomes a three-dimensional CFT. It has a chiral ring that such that the expectation values of operators in the chiral ring parameterize, well, they give you holomorphic functions on the Coulomb branch, but it has much more than that. It has a chiral ring in every complex structure. And so in principle, you can get complex coordinates in every complex structure, which is tantamount to that plus a description of, that gives you the whole, yeah.
Chiral rings are all Poisson. So you have like a P1 of syntactic structures, and then by some fairly fiction, it should be back to the other structures.
Yeah. And you can see immediately that it's a cone, well, because there has to be scale invariance. So there are no, simply because all of the couplings that could have entered the story have dropped out. The m's and t's are 0, g is infinity. So once you get to the CFT, there's no scale invariance in the theory whatsoever. Or sorry, there is no scale dependence whatsoever. And so the moduli space has to be a cone. And there's a so-called dilatation operator in the CFT, which gives you the contraction along the cone direction. Thanks.